I don't know, I try to panic and find some ways to attack this whole issue of continuity, so here I go. Let's let f of x be equal to this rational expression. Let's determine a function g that agrees with f for all values of x other than 2, but is continuous everywhere. Now, I make the assumption that you've read this section of text, you understand that rational functions as well as quadratic, excuse me, I misspoke. Rational functions as well as polynomial functions are continuous over their entire domains. That's an immediate consequence of your basic laws of limits. Albeit, if it is polynomial only, then it's continuous everywhere because that is its domain. So I don't know, everybody, do you agree that since these two upstairs and downstairs are polynomials, they are continuous everywhere? Therefore, discontinuity only occurs at x equals 2. But when I try to value the numerator when x is equal to 2, I get a 0 value. That means x minus 2 is a factor of the numerator. So maybe I could just factor that numerator. Because we are pre-calculus experts, let's just dive into it. Using synthetic division, I'll factor that beast up there, understanding that x minus 2 is one of its factors, clearly. Whoops. We do need to know basic arithmetic. So that being the case, if I cancel upstairs and downstairs that factor of x minus 2, here's what's left over. But when x is equal to 2, that evaluates to a 4 plus 2 plus 3. Is that a 9? So to answer my own question, I will define g to be a function whose output is f of x, as long as x is not equal to 2. However, if x is equal to 2, then the corresponding y value should be, what did I just say, 9? Now, this function g is continuous everywhere and agrees with f for all values of x other than 2. Now, this is why I refer to this kind of discontinuity as a removable discontinuity, where I had an open dot in the graph, or an open dot in the graph and a closed dot somewhere else above or below, because I was to remove the discontinuity by redefining my function at a single value of x so that I do maintain continuity, at least at that particular value of x, but in this contrived example, at all values of x.